All right, so we're going to look at proof by induction for divisibility results. So if you recall from sort of previous videos, what proof by induction is, I think a good analogy just to remind us is the idea of sort of an infinite ladder. If you can place your foot on the first rung and then you can show that you can get to every other rung on the ladder from there, then you're able to prove that it's true, that some rule is true generally. So let's look at this example. It says use mathematical induction to prove that n cubed minus n is divisible by 3 for all n, where n is a natural number. Remember, natural numbers, whole numbers greater than 0. Sometimes including 0, but generally if it doesn't say it includes 0, then it's just all positive whole numbers. So the first thing we want to do, if we just go through our steps again, is to outline the proposition P of n for some natural number n. And so our proposition would be this. So let P of n be the proposition that n cubed minus n is divisible by 3 for all natural numbers n. And that's just basically restating what the question's asking. Okay, this first step is to show that the base case is true. So in the first instance, we would have n being 1. So P of 1 would be 1 cubed minus 1, which is 0. And 0 is in fact divisible by 3. 0 divided by 3 is 0. And there's no remainder, right? So that means it is divisible by 3. And so we can say that the base case is true. So we've kind of got our first foot on the ladder. And then what the process of proof by induction says is assume that P of k is true, where k is some natural number. So now we're going to say, all right, let's assume that this is divisible by 3 for some natural number k. And so basically that's just going to look like this. P of k equals k cubed minus k, which equals 3m. Now what that 3m means is this right-hand side, or the whole thing, is divisible by 3. If it's a multiple of 3, then it's divisible by 3. So m, where m is some integer. Okay, so it could be positive or negative there. Okay, so then our next job is to prove that we can get to the next step on the ladder. So if we do that, we need to show that P of k plus 1 is true. And yeah, I think this is interesting. So let's do that. Let's evaluate the proposition of P of k plus 1. So we're going to get k plus 1 cubed minus k plus 1. So just subbing in k plus 1 here. Expanding this, this is a quadratic multiplied by a linear factor. Trust that you can work this out. K cubed plus 3k plus 3k plus 1 minus k plus 1. All right, simplifies to this. K cubed plus 3k squared plus 2k. You notice there's a common factor of k there. So take k out as a common factor. You get k multiplied by k squared plus 3k plus 2. Okay, and then you can factorize this right-hand side. What multiplies to 2 and adds to 3? Well, 2 and 1. So this is going to factorize. This quadratic here factorizes to k plus 1 times k plus 2. And so we get P of k plus 1 equals k times k plus 1 times k plus 2. And you're probably wondering, well, why is that important? Well, we know that k is a natural number, and we know that this is just 3 consecutive natural numbers. So for example, k could be 3. So k is 3, k plus 1 is 4, k plus 2 is 5. One of those numbers, if you've got 3 consecutive numbers, has to be divisible by 3. So this thing must be a multiple of 3. No matter where you start, if you've got 3 consecutive numbers, one of those numbers has to be divisible by 3 because, as you know, 3 times tables, 3, 6, 9, 12. Every third number is divisible by 3, right? So if you've got 3 numbers, one of them is divisible by 3. Okay, I think you get the idea. So then what we can conclude is there's actually another way we could have shown this, but I think that's a satisfactory explanation that this has to be divisible by 3. Alternatively, we could have taken k cubed minus k. We could have recognized k cubed minus k appearing somewhere here. And since we're assuming that it is equals to 3m, we could have substituted that in. But I think this is a satisfactory step. Let me know if you think otherwise. In any case, conclude that Pn is true for all natural numbers n. So, by the principle of mathematical induction, we have proved that P of k is true, and P of k plus 1 is true for every natural number k. So, yeah, hopefully you found that interesting. It feels a bit mystical. I still think it's really cool. that, yeah, we can just show that if we can prove the base case and then we can get to every rung on the ladder, then we can make some pretty cool conclusions about divisibility in this case, but also can be applied to a whole range of other problems. So we'll come back later on and we'll talk about some of those other problems, but good luck for now, and I'll talk to you soon.